Okay, so in this segment, we're going to offer another example of the kind of reasoning we looked at last time. As I mentioned earlier, it's called Bayesian reasoning because it can be done through a formula called Bayes' theorem, which I'll mention briefly. So here's the problem. This is a problem that was on your homework. Suppose that a cancer test will produce 99% true positive results for people with a particular kind of cancer, and 99% true negative results for people without that kind of cancer. So it's 99% accurate. And let's suppose further that only 0.5% of people have that kind of cancer. And let's suppose further that we randomly test somebody. We're not testing this person because they have symptoms or anything. We're just randomly testing somebody. And suppose that individual that we randomly tests positive. What is the probability that that person has that kind of cancer? Well, most people ignore the base rate. They ignore the 0.5%. They don't really know what to do with it, or they give it a little tiny bit of weight and say that the probability that the person has cancer is very high. They might say 99%, they might say 90%, they might say 80%, but that's wrong. So it's just plain wrong. The probability that the person has cancer is about 1/3. So why is that? Well, here's an explanation. The test is 99% accurate, which means 99% of the time the test says no if the patient doesn't have cancer, and 1% of the time the test says yes even if the patient doesn't have cancer. And 99% of the time the test says yes if the patient has cancer, and 1% of the time it says no even if the patient doesn't have cancer. Now suppose 0.5% of people have the cancer. Then, in a random sample of 1,000 people, 995 of them won't have cancer and 5 will. Now suppose we have 1,000 people take the test. For the 995 who don't have cancer, roughly how many times is the test going to say yes, that they do have cancer? Well, it gets it wrong about 1% of the time. It gets it wrong about 1% of the time, so it's going to say yes for about 10 of them. For the 5 who have cancer, roughly how many times will the test say yes? That is, how many times will it capture them? Well, the test gets it right about 99% of the time, so it's going to get pretty much all of them right. It'll be a little bit below that, but since we're working with small numbers, we're going to round and we're going to say 5. So how many total times will the test say yes? Well, it's going to say yes for 10 of the people who don't have cancer. It's going to say yes for 5 of the people who do have cancer, so you're going to get about 15 total yeses. And then how many of those total yeses are people who actually have cancer? 5. So 5 out of the 15 people who test positive will actually have cancer. So if you test positive, the odds are about 1/3, 1 in 3 that you have cancer, 5 out of 15. So the numbers are filling in now. I'm just going to go through it again. For the 995 who don't have cancer, it's going to say about 1% of them do, so it would be like 9.95. We're going to round to 10. For the 5 who have cancer, it's going to say 99% of them do. That's going to be 4 point something high. We're going to round to 5. How many total cases? Well, those 10 up here who don't have it plus the 5 who do, it's going to be 15 total cases. How many of those cases actually have cancer? Well, it's those 5 who do have it and test positive. So what are the odds you have cancer if you test positive? 5 out of 15, which is 1 out of 3, which is 33%. Here's another way you can think about it. This is using Bayes' theorem. I think it's better to do it the intuitive way because in order to understand what to plug into the formula, you have to be able to do it the intuitive way. So the theorem doesn't really help you unless you can do it the intuitive way. But once you can do it the intuitive way, the theorem can maybe in complex cases help you do things more quickly. Here we have the probability that you have cancer given a positive test, an affirmative test. And that's going to be identical with the probability that you get an affirmative test given that you have cancer multiplied by the probability that you have cancer divided by the probability that you get an affirmative test. Now that's a mouthful. I don't expect you to understand it perfectly immediately. Let me say one thing really quickly here. Notice that we're looking for the probability that you have cancer given that you've tested positive. It's like, I tested positive. Now, given that, what are the odds I have cancer? That's what this number is representing. Over here, we have the probability that you would get a positive test if you did have cancer. And the first thing I want you to see is this, the probability that you have cancer given that you tested positive, is not the same thing as this all alone, the probability that you have affirmative test given that you have cancer. In order to get from here to there, you need to use this other stuff. Now, just to see that these are different, think about the probability that you're a sister given that you're a sibling versus the probability that you're a sibling given that you're a sister. The probability that you're a sister given that you're a sibling is 50%, but the probability that you're a sibling given that you're a sister is 100%. So that's the first thing to see, that take the probability that you have neck pain given that you have spinal meningitis is very high, but the probability that you have spinal meningitis given that you have neck pain is very low. So I want you to first just understand the difference between the probability that you have cancer given that you test positive and the probability that you would test positive if you did have cancer. So think through that and make sure you have that clear. You can use the sister-sibling example. You can use examples like this, the probability that someone is married given that they're a bachelor. Or sorry, let me rephrase that. The probability that they're unmarried given they're a bachelor, the probability of that is 100%, versus the probability that they're a bachelor given that they're unmarried. Well, the probability will be 50% because only males who are unmarried count as bachelors, at least according to the standard definition. Okay, so again, think through the difference between this thing and this thing. And then what I want you to do next is start to think through how this thing relates to this whole thing over here. So what is this whole thing over here? Well, the probability that you have cancer unconditionally, that is, there's no given that, it's just the probability that you have cancer, not given anything in particular, just given no further background information, is just the prevalence of cancer in the population. So this is like your 0.5%. It's just the background frequency, it's the base rate. This thing down here is like the total number of positive tests. It's like the probability of getting a positive test, whether you have cancer or not. So this is just like the total positive tests from people who have cancer plus the total positive tests from people who don't have cancer. So here we have the background frequency, the 0.5%. Here we have the total number of affirmative tests, which in our example with 1,000 people was 15. And up here we have the accuracy of the test. This is like the descriptive information, the thing that is sort of predicting what we want to know. So the probability that you'll get an affirmative test given that you have cancer is 90% because the test is 90% accurate. So we take that 90%, we combine it with the probability of cancer, which is 0.5%, and we combine that with the probability that you would get a positive test, which is basically 1.5%. And so we do this, we take these three numbers, our 99% accuracy for the test, our 0.5% base rate, and our 1.5% probability of an affirmative test, the total number of positive tests taken as a percentage. And we combine those, and when you do the math after you combine them, you get 33%. Now, I've only talked about what's down here. Why did I put this thing up here? It's because I want you to see, we won't really be doing this until much later in the semester when we talk about scientific reasoning, but I want you to see that this thing here can be sort of put in a general way. And then the general way is this. Often in science, what we want to know, or in daily life for that matter, what we want to know is the probability that some hypothesis is true, or some theory is true, or some claim is true, given the evidence that we have in front of us. So we're looking at some evidence and we want to know how probable is this hypothesis given this evidence. And that's kind of like wanting to know how probable is the hypothesis that I have cancer given the evidence that I've tested positive. And what we do if we want to know this thing is we look at the probability we would get the evidence if the hypothesis were true. That's like the accuracy of the test, the probability we'd get a positive test if the hypothesis that I have cancer is true. We multiply that by what's called the prior probability of the hypothesis, how probable we should have thought it was even prior to getting the evidence. That's like how probable we should think it is that I have cancer prior to me taking the test. Well, it's 0.5% because that's the percentage of people in the population who have the cancer. And then we divide by the probability that we would get that evidence, just like we divide by the probability that we would have a positive test, whether we have cancer or not. Now, later on when we do the scientific reasoning portion of the course, I'm going to spend some time trying to make you sort of feel in your bones that this is plausible. That is, I want you to just intuitively understand why making this number or this number go up would make this number go up, and why making this number go down would make this number go up. That is the number you get over here go up. So all of it should just, once you understand why making this go up should make this go up, and why making this go up should make this go up, and why making this go down should make this go up, then this formula will start to feel really intuitive. Right now, that's not the goal. Right now, the goal is just that you see there's a formula that corresponds to the sort of mechanical way we were figuring out the answer to the problem earlier. Okay. So let's do this one more time, and then we'll stop this segment. We have a doctor who tells the patient after testing positive on the 99% accurate test that you almost certainly have cancer, and the patient says, oh no, and then we want to correct this doctor's mistake. So we say 0.5% of people in the population have the cancer. If you have the cancer, then the test says you have the cancer 99% of the time, and if you don't, it says you don't 99% of the time. 1,000 people take the test. How many of them will have cancer? Well, 0.5%. What's 0.5%? Of 1,000, it's 5. For the 995 who don't have cancer, how many will test positive? Well, 1%. What's 1% of 995? It's approximately 10. I know I said before this symbol stands for not. It's also used for approximately. I'm using it for approximately here. And I guess for the 5 who do not have cancer, how many will test positive? Well, 99% of them. Or sorry, for the 5 who do have cancer, how many will test positive? 99% of them, because the test is 99% accurate, so that's going to be about 5. How many total positive tests? It's the 5 plus the 10, so it's 15. How likely is it that someone has cancer given a positive test result? Well, 5 people in the population do have cancer and test positive. 15 total people test positive. So it's 5 out of 15, which is 33%. So approximately 33% of the odds. And of course, the doctor should say, oops, let's make that 33%, and the patient might have a little more positive attitude after testing positive. So here's the immediate lesson. When assessing how probable a theory is in light of some evidence, or like the theory that you have cancer, you should always consider how probable the theory was prior to the evidence and weigh the new probability by that old prior probability. And Bayes' theorem gives you a way to do that, but more generally, the strategy that we're talking about here gives you a way to do that for particular kinds of cases. And we'll say a lot more about Bayes' theorem and the way to think about it when talking about scientific theory confirmation as compared to the way to think about it when talking about cases like this cancer positive test toy example, because there are sort of important differences. But for now, we're going to stop there, and we'll continue next time with some more examples to help you get comfortable with this way of thinking.